pKa is at the half equivalence point. And so what we can do is figure out what the equivalence point is. The equivalence point is always where we have this sharp jump up. So I would say that that's at 25 mils. So our half equivalence point must be at about 12.5 mils. Okay, that's what we mean by half equivalence point. So if we go here and walk up, we can see that the pH at this point is about 4.8, give or take. And so 4.8 is going to be equal to the pKa. So the Ka is just 10 to the negative pKa. Which ends up being about 1.8 times 10 to the negative 5. Which is E. So I think if you can remember this part, you'll be in a good spot. Or if instead you remembered that the pKa is at kind of the middle of this flatter region, then that would also get you there. Okay, for number 21, they give us the Kas relating to phosphoric acid dissociation. And they want us to identify the strongest base in any amphoteric species. Okay, so we know that the strongest base will come from the weakest acid. Okay, and so looking at the Kas, we know Ka3 is the smallest, which means HPO4 2- is going to be the worst acid, making PO4 3- the best base. Okay, so we can already eliminate 3 options there. Amphoteric means that we can either act as a base and pick up a proton, or we can act as an acid and give off a proton. And so when I look at these, I see that this could pick up this proton and act as a base to form the H3PO4, or it could do the reaction below and give up a proton. So I'd say that H2PO4- is amphoteric. And then I'd say the same thing for HPO4 2-. Whereas like the PO4 3- can only act as a base. Doesn't have any protons to give up. And H3PO4 can only act as an acid. Okay, so then E is the correct answer here. So a little bit of vocabulary. For number 22, they want us to figure out if the given mixtures will make a buffer or not. So to be a buffer, you need a weak aster base, and you need to have its conjugate. So you need to have both the weak thing and its conjugate together in solution. And so when I get to these problems, my first pass, I always just look for something obvious where you would have a weak acid or base and its conjugate salt given. We don't have that in any of these cases though. We always have something strong as one of the components. So what we'll have to do is go through and think about what happens after whatever we're given reacts with the other component. For the first solution, we have HCl and NaOH. And because we've memorized all of our strong stuff, we know that these are both strong species. And so we'll never have a weak acid or base and the conjugate present. So we can get rid of those. In B, we have sodium fluoride and HCl. So sodium fluoride does dissolve to form Na plus and F minus. And F minus is a weak base, and it's the conjugate of HF. And so what we can see is after the fluoride reacts with the HCl, which I'll just write as H plus because it's a strong acid, what's left over? Okay, so whenever we have a reaction, we need to work in terms of moles and have an ICF table. For sodium fluoride, we'd have for the fluoride, 0.05 moles. And that would also be true for the acid. So they're both our limiting reagent, so they'd both be totally used up to leave us with 0 of each. And we'd form that much of the HF. Okay, so this is what would happen in the reaction. So we can look and see, do we have a weak acid or a weak base? Okay, we have the weak acid, but do we have its conjugate base? And the answer here is no, because it was totally consumed in the reaction. So B is not an option. Okay, for C, we have a weak acid. We're mixing it with a strong base. And so again, we'll have to see what remains after the two of them react. So we have HF plus, and I'll just write OH minus for the strong acid, or strong base. And they react to form water and fluoride ions. So whenever we have a reaction, we work in moles and we use an ICF table. Okay, so initially for HF, we'd have 0.025 moles of HF and 0.05 moles of the base. Ignore the water. 0 of the fluoride. Then we look to see which is our limiting reagent. And because the reaction is 1-to-1 and we have fewer moles of HF, that will run out first and be totally consumed. We'll use that much up of the OH minus. and gain that much of the F minus. Okay, so then we do our check. Do we have a weak acid or base and its conjugate? We have a conjugate, but we don't have the weak acid. We used it all up. So C is also not a buffer. Okay, for D, we have the same components, just now in different amounts. So we can use our ICF table to see what we would be left with. So we'd have 0.05 moles of the HF in solution, 0.025 moles of the OH minus. None of the fluoride to begin. And now our limiting reagent is the hydroxide. So we'll use up all of the hydroxide. It will run out first. And then we'll take that much away from the HF. And then that much will become fluoride. Okay, so now we ask, do we have a weak acid or base? Yes, we have HF. Do we have its conjugate? Yes. Okay, so D seems to be pretty promising. Let's check E. So in E, we'd have F minus present in solution, and then we'd have OH minus from the strong base. And these would react. We generally don't think of bases reacting with each other, right? So we have the wrong components here in general. We would only still have that. And these aren't going to combine to somehow magically make HF. So E is out. And D is the correct answer. Okay, so buffers. Weak acid or base, conjugate. And then the buffer will resist changes in pH, and we can use the Henderson-Hasselbalch equation. Okay, number 23, it's asking us which of the following acids would have the highest pH at the equivalence point of its titration. Okay. So highest pH would be most basic, of course. And so let's think in general about what's happening. In the titration, we're starting with some acid, we're adding some volume of base to it, and we monitor how the pH changes. Okay. Something that's good to know is that when a strong acid and base are at the equivalence point, so if you have a strong acid and a strong base, the equivalence point is always at a pH of 7. Okay. But if we have a weak acid and a strong base, we have a different kind of titration curve, where we start acidic, so low, increase, then we kind of level out a little bit, and then we have a sharp increase. And the equivalence point is still at that inflection point. But now what's true at the equivalence point is that we used up all of the weak acid. And we used up all of our base, but we're left with our conjugate base in water and some negligible counterion like chloride. Okay. And the equivalence point will be greater than 7 when we have a weak base being titrated with a strong, when we have a weak acid being titrated with a strong base, because we have that conjugate around. Okay. And it'll be even higher, right, if the A minus is stronger. So higher pH if we have a stronger conjugate base, which would mean we need a weaker acid. And so we want to figure out which of these is the weak acid, or the weakest of the acids. And so, before we even look, we can get rid of HCl. Okay. And because pKa is equal, or let me put it this way instead. Because Ka is equal to 10 to the power of negative pKa, they're going to go oppositely with each other. So that tells me that the weaker acid, which would have a smaller Ka, will have a higher pKa. And if you don't like using this logic, you can use the pKa's to calculate Ka's for each individual one. But what I'm just going to do is say that the acid with the highest pKa will be the weakest acid and will give us the strongest conjugate base. And so there's one acid on this list that clearly has the highest pKa and would be the weakest, and that's C. This HCN. Okay, so just remember that at the equivalence point, you have the conjugate base left over, and a stronger conjugate base will come from a weaker acid. And you can use the Ka's to help you pick out the weakest acid. Okay. Here we have aspirin. Someone must have had a headache when writing this exam, because this is the second painkiller we've seen. So we're taking aspirin and adding NaOH to it. So here they give us the acid dissociation of aspirin. So if we add NaOH, what can happen is that the acid here, the H3O plus, could react to form water. Right, that's what we've been talking about for weeks now. And if that happens, we're essentially removing a product. And when that occurs, we shift the reaction to the right toward products, just based on Le Chatelier. Okay, so keeping that in mind, let's go through these options. So the first one says Ka will increase. So we learned in exam 2 material that pretty much the only way to change an equilibrium constant is important here, is to change the temperature. So unless we change temperature, nope. Okay, delta G will decrease. So let's remind ourselves that a more negative delta G, which would be smaller, means that it's more likely to proceed toward products. And that's what's happening up above when we remove some of the product from solution. So 2 seems to check out. And so with number 3, we're saying that pH will increase. So this on its face just seems like a good option, right? Because we're adding a strong base to it. But also we know in that process we're neutralizing some of the acid. So pH increasing makes sense. The 4th choice says that the concentration of aspirin will decrease. And we already decided that the reaction is going to shift toward the right. And so some of this aspirin will be used in that process. So this also makes sense. And then 5 says the reaction will shift to the left. We've already talked about why it shifts to the right. Okay? So the middle 3 are all correct, corresponding to answer B. "25. Jessica happily performed the following titration." Where do they find these people to perform titrations happily? Am I right? Okay, never mind. Titrations are good. Okay, so we're titrating methylamine with HCl. And they want us to tell what's in solution at a pH of 10. So I've marked that on the curve. So we can go ahead and just write the reaction too to help us keep track of what's going on. Okay. So at a pH of 10, we're still basic, right? We're above 7. So there's no way that H plus is going to be present. Okay. And so the equivalence point is somewhere there. And so that would tell me that HCl is still limiting. So we use up all of the HCl. And we still have, at this point, excess base. So we still have some of this around. But we have reacted some of it with the HCl. And when that happens, we make some of that conjugate acid. And then, there's chloride floating around minding its own business. Okay. And so these are the only 2 species that are present in abundance in the solution. Okay? Because these are the only 2 that would be left in the reaction. So it's going to be option choice D. Okay, so you guys have now completed practice exam 3C. And like I've mentioned, this is our first time doing the practice exams this way, so let us know what you think about it. If you hate it, tell us. If you love it, tell us. And we're also not using the most state-of-the-art technology, so if you think it's worth us, following through with this, but maybe with a little better of a stylus or something, let us know. And maybe we can make improvements in the future, too. And so don't forget, there is a light at the end of the tunnel, and you guys are more than ready for this exam. You've been working on the material, been going to lecture, doing homeworks, LA worksheets, all kinds of stuff. And you can do well on this, okay? So keep up the positive attitude.